Okay, so off we go. Here's where we left off last time. So I want to talk about this diagram a little bit. This is not in the book, but I think this is a really, really useful collection of ideas. I drew a extremely compacted version of the diagram here in the notes, but y'all have access already. Of course, if you go to the class web page, just the one for our sections. There's a link section in there called class resources, I think it is, something like that. And this file is called diagram.pdf. So y'all can download this at your leisure, and I encourage you to do that. This is what I'm going to work off of because when you typeset, you can get more cleanly visible on the page. It's easier to work with. Okay, so here's the idea. Y'all may recall I've mentioned before that what we're showing y'all in this course is a bunch of separate theorems, as kind of in the form that they were developed independently of each other. But it turns out that a bunch of the theorems that we're seeing in this class were subsequently found to actually all be separate special cases of the same unified single theorem. And a really great way to learn multivariable calculus would be to talk about that unified theorem. The problem is it's sophisticated and it has a tremendous amount of machinery that has to be built up. It's kind of abstract and pretty unsatisfying, certainly to first-time learners, and especially if you're not a math major looking to learn about abstractions and stuff like that. That's really unfortunate because seeing how all of the theorems that we're going to learn are in fact literally special cases of the same single theorem, there's a lot of value in that. So I like to kind of do a little bit of the best of both worlds. We're presenting these theorems, of course, very concrete ways. We're Green's theorem in R2, talking about vector fields and circulations and stuff like that. It's all very concrete. But what I'm going to do is take a lot of the formalities and abstractions that are necessary to develop for the unified theorem, right, and boil off all the formality and all of the abstraction and the clunky, bulky notation and stuff like that, and leave just some of the underlying structures that just show how these pieces fit together. So what I'm left with is this diagram, and this is not, I'm not going to prove anything that's written here, right? I'm just going to suggest that because of where this diagram comes from, because this comes from how these theorems truly do fit together, right, in important and meaningful ways, if you just kind of trust the way that this diagram is organized, and if you organize the ideas in your head this same way, then you're going to find that there's just so many different bits of good fortune and pleasant coincidences and convenient symmetries and just lots of good news. Lots of good things will happen if you just organize the ideas in this way. So let's talk about what's on the diagram and what is the organization I'm talking about. I'm going to start with this line right here. You'll notice I have what I'm calling boundary operators there, and I hope this is geometrically appealing. If you have a two-dimensional, two being the indication of dimension, two-dimensional region, and if you ask what is its boundary, well, it's going to be a curve, which, of course, is one-dimensional. All right. And then if you were to do the same thing, take a curve, one-dimensional, of course, and if you talk about its boundary, you're going to get some points, which, of course, are zero-dimensional. All right. Now, what kinds of calculations have we done on two-dimensional regions? Well, we've done double integrals. What kinds of calculations have we done on curves? Well, we've done line integrals. And now again, I'm going to restrict our attention to vector line integrals. And why is that? Well, it's because when you take this more sophisticated theorem and boil off and look for just, what is the actual version in our, concrete point of view of what is actually happening here, it just happens to be vector line integrals. It's just how the cookie crumbles. And again, I can't tell you why, because that's exactly what I'm trying to avoid, right, is having to go through all the formalities and stuff. So this is just kind of what is. And then what kind of calculations have we done at points? Well, that's where we evaluate functions, I guess you might say. So now, likewise, when we do a double integral, our integrand is a function. When we do a vector line integral, our integrand is a vector field. When we plug a point into, well, what do we plug it into? A function. So plausible, perhaps, that we should think of these things being there. And you may recall long ago I suggested that we would have good reason in the future, and here we are, to compose these operators. Gradient, that turns functions into vector fields. Green's operator, that turns a vector field into a scalar value function. So now again, I have not proved anything there, and I haven't really hardly justified anything about what I've written down up there in that part of the diagram. But if you were to develop all the sophisticated ideas that I'm waving my hands at and boil off the formalities, this is what would be left. So I'm going to claim that this is actually a natural way to organize these ideas. Now, what I'm going to try to do now is, even though I can't show you any of that natural stuff, what I can do is show you some of the wonderful patterns that show up just as a result of organizing these things in this way. So here we go. Let's talk about the fundamental theorem of line integrals. What does the fundamental theorem of line integrals look like? And, well, what we do with the fundamental theorem of line integrals, you take some function and you compute its gradient. You take a curve and you think about its boundary points. You evaluate, in this sense, the original function at those boundary points, like so. You compute a vector line integral of the gradient that you just computed on your original oriented curve, like so. And the big punchline was that those two sides are the same. Now, again, this does not prove anything. This doesn't demonstrate anything. The reason I put this up on the board is to show you, I'm going to say what the pattern of this theorem is in this diagram. The fundamental theorem of line integrals follows this pattern that you kind of push to the right in your integrands. You sort of push to the left on your domains. You evaluate on both sides, and you get the same thing each way. So that's the pattern that I claim represents the fundamental theorem of line integrals. Now keep that in mind. And now let's think about Green's theorem. Green's theorem, there's a vector field for which you compute Green's operator. There is a two-dimensional region whose boundary you consider. And, reminder, a line integral of your original vector field around that boundary, a double integral of Green's operator on your original domain, and those are equal. So this is where it starts to become what I like to call an eyebrow raiser. This is weird that this pattern that represents what the fundamental theorem of line integrals looks like is exactly the same pattern that represents what Green's theorem looks like. That's weird, isn't it? Right? So I hope that, now this is tip of the iceberg. I hope the fact that these two theorems, totally different theorems about totally different objects with totally different geometry, right? The fact that they look, the diagram exactly the same should make you suspicious. Maybe willing to believe when I say that these theorems are actually kind of the same theorem. Right? Okay. All right. Now, just to persuade you further, I hope, there is also a diagram for R3. We're going to get into the R3 stuff later today. Just a few minutes. So we haven't defined the objects that are on this R3 diagram yet, and we'll get to that. Fine. It's going to take a little bit of a while to develop all those concepts and stuff. But this pattern, that we developed here for the fundamental theorem of line integrals that we were so surprised to find is the exact same pattern for Green's theorem, right? Oh my God, what are the odds? The same in both cases. Well, it's true down here as well for the three-dimensional fundamental theorem. It's true down here for what we are eventually going to call Stokes' theorem, Stokes' curl theorem, to be more precise. And it's true over here for what we're eventually going to call Gauss's divergence theorem. So it's not just these two theorems up here. There's kind of 5 theorems that are all the same pattern on the diagram. And again, then I hope you'd be willing to believe when I say they're really, I mean, honestly, morally, they're the same theorem, just in different contexts. And by the way, there is a 6th one as well, the fundamental theorem of calculus. If you were to make a one-dimensional version of these diagrams, the fundamental theorem of calculus follows the exact same pattern if you interpret appropriately. Okay, now there's more. Let's see here. Let's talk about our special vector fields that we've discussed at quite a bit of length. Specifically, we've talked about gradients, vector fields that are gradients of some function. Now, they're special in various ways. One of those ways that we saw last time is gradients are irrotational, namely Green's operator is 0. They're also path independent. And path independent is a hard thing to kind of represent on this diagram. Here's my best take. Path independent says that if you have 2 curves that have the same boundary points, namely they start and end at the same point, then you get the same value for the line integral. So these 3 different colorings represented on the diagram, they all describe the same vector fields. Regularity issues aside, I don't want to worry about the singularities and discontinuities, and ignoring all that stuff. Every vector field that's a gradient is irrotational and is path independent, and vice versa, and every other direction. These are just the same vector fields that have 3 seemingly different properties, but they're all the same vector fields. Okay, so again, who cares? I've got a diagrammatic representation of something. Doesn't prove anything. Here again is where the eyebrow raiser kicks in. This pattern here, describing path independence and gradients and irrotational, etc., etc. Same thing works in 3 dimensions, but with curl instead of Green's operator playing the role of irrotational. And here's the really weird one. This is the one that I think is really quite strange. And a lot of students don't get to see this. A lot of multivariable calculus courses don't show you what I'm about to show you here. And that is that you can even increase the dimension like this. And what we're going to find, and just for foreshadowing purposes, I'm going to zoom in and talk this through. Vector fields that are curls of something, it turns out, will always have divergence equal to 0, and will be what I am going to suspect you might be willing to believe should be called surface independence. So again, completely different ideas, completely different properties than what we were talking about previously, but they lay out on the page exactly the same way. And again, that should make you highly suspicious that there's deeper stuff going on here that we're seeing sort of just the shadows of in this class. And furthermore, and where y'all are, I hope will be really particularly sold on the value of this diagram, what this means is you don't have to learn, I mean, you kind of do, but to a certain degree, if you understand this pattern as it pertains to path-independent vector fields, as you're learning all these other ideas here that we'll be talking about much later, Same pattern, and what you understand about path independence will help you understand surface independence. And will help you understand the arguments that we're going to make about, why is a curl? Why does it have divergence equal to 0? And these other kind of related ideas. The patterns just keep holding over and over and over again. So I am a huge fan of these diagrams. Again, this is our R2 diagram for the ideas that we've been working on so far. And coming up real soon, next week, we will be developing ideas on this R3 diagram. And I think you are extremely well advised to always keep these diagrams in mind. All the ideas that we talk about, kind of have a copy of this diagram, that you can, just to your left, that you can just kind of refer and just kind of keep track of where you are on the diagram as we talk about all these ideas. Use this diagram as kind of an indexing for your organizational system of how you sort these ideas in your mind. And everything will just fit together in seemingly lucky ways that you'll be able to benefit from. Okay, so I really hope this is useful, and we'll be referring back to this as we go on through the course. Okay, so that's all this stuff. Let's talk about how to find antigradients. I kind of glossed over this previously. If you want to use the fundamental theorem of line integrals, of course you need to know what the antigradient is. That's the whole formula. Right? So you need to know what is this. What is this little f? That's the antigradient. And the big idea goes as follows. If your vector field is an antigradient, then the coordinates of f are the coordinates of the gradient. So, for example, the partial of f with respect to x is p. Which, by the way, you can kind of phrase backwards. And f must be the x antipartial of p. So make sure you're comfortable with my claim here. These are just the same statements made sort of grammatically backwards. Right? Basically the same idea. Okay. Likewise, of course, for the second coordinate, and likewise, of course, for the third coordinate. Okay, now, keep in mind when you take antiderivatives like I have here, what I have left outside of the highlighting here is, I'm sure you all had this drilled into you when you were in single variable calculus. When you take an antiderivative, you always have to say plus c. Right? So why do you have to say plus c? Well, because if I were to just say this is my f, and I cite the fact that, look, when you take the x derivative, you get p. Well, keep in mind, any constant that I added in here, when you take the x partial, that x partial would make the constant disappear and still works. So you can add any constant because you're taking a partial. Partials of constants are 0. But here's the thing. Functions of only y and z also, when you take the x partial, will also disappear and therefore still work. Right? So it's a little sloppy, a little too quick to say that f is, whatever anti-partial you might happen to arbitrarily write down for sort of algorithmic convenience reasons. In fact, f could be any of these x anti-partials. And any function of only y and z with no x's in it, still going to satisfy this equation right here. Right? Okay, so just for your cultural awareness, these are sometimes called partial constants. Very natural language. Okay, so here goes the game then. Now keep in mind our goal with all of this is to find the antigradient, right? We're trying to find this function f. And, well, f has to equal to all three of these things, as we've discussed. And if f needs to equal to all three of these things, then all three of these things need to equal to each other. And that's going to be the game that we're going to try to play. We're going to write down the antipartials. We're going to write down what our partial constants are allowed to be, and we're going to start to play the game of how can I make these three things all equal to each other. And here we go. Let's do one. So following the pattern, we take the x antipartial of P. We take the y antipartial of Q. We take the z antipartial of R. That's just following the equations from the previous page. Those are easy computations to do, right? Nothing to it, easy antipartials. But don't forget your partial constants, right? And thus begins the game. I need to figure out how can I make this equal to this equal to this. And, it's just a little puzzle. So now here's what I propose first. I do notice x squared y there, and I feel like there ought to be an x squared y right there, but there isn't. Why is there no x squared y there? You know what we could do? This thing here is allowed to be x squared y. Let's just call this function here x squared y. And we're good, right? That term then, x squared y, is in all three of these expressions that I need to make equal to each other. So we're making a little bit of progress. Let's continue. I have an xz there, an xz there. No xz in the sort of gap where you would kind of have hoped it would have appeared, but you know what? It could be that function right here. Keep in mind, C2 could be any function of x and z, such as xz. So now we've got that term in both of them, and you can see this coming. That is equal to that, which isn't explicitly where I wanted it to be, but it could totally be that. And so sure enough, I have arranged now for all three of these things to equal to each other, and then f is that thing that they're all equal to. And I've found myself an anti-gradient. Anybody see how that game works? Okay. All right. Now, we won that game. We knew we were going to win. We could have known anyway that we were going to win because our vector field, for which we wanted to find an anti-gradient, as we've already seen, the curl was 0, and that means that there is an anti-gradient. Right? That's from last time, one of our big theorems from last time. Okay. All right, so what happens, though, when there isn't one? What happens if you know in advance that there's no anti-gradient? How does the game break down? How do you lose this game? In other words, when you're trying to find something that doesn't exist. And this is a nice little example here. Let's consider this vector field. Now I claim this is a loser because you can compute Green's operator. It's not 0, as we computed last time, and therefore there is no anti-gradient to be found. Right? So you shouldn't find an anti-gradient when we know for a fact there is no such anti-gradient. So how do we lose this game? Well, here's how the game breaks down. You take the first coordinate, take the x antipartial, you take the second coordinate, you take the y antipartial. The usual story. There are those antipartials. Here's your partial constants. Thus begins the game. I need to make this equal to this. I get to pick whatever I want for that function, as long as it's only a function of y. No x is allowed. And I get to pick whatever I want for this, as long as it's only a function of x. No y's allowed. And try to play that game. And you're going to lose. Right? Entertain yourself as long as you continue to be entertained by it. But there's nothing you can put into these spots and make these two things equal to each other. So no anti-gradient. How are we doing? Is everybody on board? Okay. Moving along. That finishes chapter 6. Off we go to chapter 7. So, again, a little context. Chapter 7 is kind of about three-dimensional versions of chapter 6 theorems. Like, so chapter 6 theorem, we have Green's theorem, for example, Right? Green's theorem takes place just in the plane. It's a two-dimensional theorem only. Two-dimensional fluids, two-dimensional circulations, two-dimensional regions with boundaries that are curves, of course, because that's the geometry. If we were in 3 dimensions, is there a 3-dimensional version of Green's theorem? And it turns out there is, and it's fantastic, and it's very cool. There's a lot of stuff that we have to develop first, though, in order to be able to talk about that. And then likewise, don't forget, we had the what we call the 2D divergence theorem, or sort of the alternate version of Green's theorem about flux instead of circulation. Is there a 3-dimensional version of that divergence theorem? And again, yes, there is, and we'll be developing that as well. But again, in order to do so, we need to develop some machinery and define some things and establish some groundwork before we can do that. So that's what we're going to do now. The first step along that direction is to talk about what is a parametric surface. And here we go. A parametric surface is really just like a parametric curve in the sense that you get position as a function of, well, if it was a parametric curve, position is a function of one parameter. Here, parametric surface, position's a function of 2 parameters. That's all it is. That's the only difference. 2 parameters determining position in space instead of 1 parameter determining position on a curve, typically, often anyway in the plane, could also be in space. Okay. All right. So here's an example. We've actually already done this. If you go back to section 1.5, you'll notice we talked about this to some degree, and also there was a homework exercise that was pretty similar to what we're about to see here. And I'm just going to write down the parameterization. This is what I'm going to call the parameterization. I claim this formula allows me to describe location on a plane as a function of 2 parameters, S and T. Now let me walk you through where this comes from. How is it that this formula generates points on this plane? Well, I have to start by presuming that I know what plane we're dealing with. I'm going to need to know a point to kind of nail down where that plane is starting. And I'm going to need to have a vector v1 and a vector v2 defining the sort of different directions that define how this plane is pointing in space. Right? Again, if you have a plane, there's kind of 2 different directions parallel to that plane. So given that, well, starting at that point x naught, I can say, hey, you know what? If I were to move in the v1 direction by some amount, and then subsequently, if I were to move in the v2 direction by some amount, I can get, well, in fact, anywhere I need to get on the plane. If you start in the plane, and you move parallel to the plane, and then again parallel to the plane, you remain in the plane. Right? And furthermore, you've got this flexibility to go kind of, in some sense, however far you need to. I've got this S here, which means I can move, as far as I need to go. Just make S bigger if you want to go farther in that direction. Right? Make S negative if you want to go back that way. And then likewise, I've got this T that allows me subsequently to go farther in the v2 direction, or if T is negative, in the backwards of the v2 direction. And so I can get anywhere I need to in that plane just by using this formula. So position is this function of S and T. Does that make sense? Everybody happy with that? All right. Okay, so this, again, parametric surface, because we have 2 parameters, and our position is a function of those 2 parameters, S and T. All right, so we're going to see several other kinds of parameterizations, ways to generate parameterizations over the next 20 minutes, I guess it is. Here we go. Okay. One little quickie point I want to make before we proceed. One thing you'll notice, because you have two parameters, right? Now S and T are both parameters. We have to kind of abandon one of our points of view, one of our sort of geometric. That's kind of a crutch in a way, right? But when we were talking about parameterizing curves, I made this pitch that you should think of the parameter T as being time. Right? It's really nice if you think of T as being time, because then position as a function of the parameter being time, position as a function of time literally is movement. That describes the process by which you trace the curve, by which you move along and kind of in some sense generate the curve. So it's really nice sort of convenient to think of your parameter as being time. Well, now we have two parameters. And these two parameters, they can't both be time. I would find it too confusing anyway to try to imagine these both being sort of their own different senses of time. It just doesn't make any sense. So basically we have to kind of abandon this idea of thinking of the parameters as being time. And that's a little bit unfortunate, but it remains, as previously stated, position is a function of these parameters. You just can't think of them as time anymore. Okay, so how to make parameterizations. Now here's a little bit of a disappointment that I had with the textbook. The textbook gives several examples of parameterizations, and it doesn't show you where any of them came from. And I think that's a problem, because y'all are mostly engineers, right? You're not going to have scenarios where parameterizations just drop in your lap. What you're going to have is you're going to find yourself interested in various surfaces at different times. And if you, for example, have let's say the top half of a sphere, you need to create a parameterization. So the book's examples all start with a parameterization and then try to help you understand how to conclude what it creates. We need to do the opposite. We need to start with a surface to be created by a parameterization and find the parameterization. Okay, so all of my examples are the latter and how to create parameterizations, and here we go. Starting with my favorite one, the graph parameterization. Y'all may remember that term. I presented as my favorite tool for parameterizing curves. The graph parameterization. The big idea was that if your curve was a graph, then you make certain choices and bam, you have a parameterization. So same deal here. If your surface now is a graph, right, keep in mind what a graph is. Important detail here. You have to have one of the variables solved for in terms of the others. That's what it means to be a graph. Right? So if that's the case, the magic trick that makes it work, whatever are your input variables, let those be your parameters. That's it. It's all over but the shouting. That one little trick. Write your surface, as a graph. Whatever function you're looking at a graph of, identify the input variables, make those your parameters. And again, I claim it's all over. Now let's see, how is it that this is all over? Let's look at this specific example. You see I have this surface here written as a graph. Y'all will recognize that, of course, as a paraboloid, right? Long, long ago, chapter 2, ancient history. That's a graph. My input variables are x and y. I'm going to let my input variables be my parameters per the trick. That gives me 2 of my 3 formulas that I need. Keep in mind, don't forget, that parameterization gives position as a function of your parameters. I have 2 of my 3 coordinates already. The missing thing is I need a formula for z. What am I going to do with z? What is z? Well, it's already determined. We actually already can just write down what z is as follows. If s and t are x and y, you plug those in right there. And if z is that given function of x and y, then that tells you z as a function of s and t. And we're done. We win. Is that cool? Everybody happy? Very algorithmic, very plug and chug. Just follow the rule. Make sure that your surface is a graph and write it as such. Identify the input variables and make those the parameters. Plug that into your formula to get your remaining formula. Nothing to it. All right. Now, just a couple more examples. There's nothing magic about the alphabetical order. The last alphabetical order variable doesn't have to be a function of the first two. You can put them in whatever order you like. So, for example, if y is a function of x and z, all good, no problem. So let me skip over one detail here and start with this right here. Notice we have a graph. Y is a function of x and z. So this is a graph. My input variables are x and z. We let those be our parameters. So again, we're 2 out of 3 done already. And if y is a function of x and z, and if x and z are s and t, then unavoidably y must be that. And again, victory, we have position, x, y, z, as a function of s and t. So, parameterization. How are we doing? Is everybody on board with that one? Okay. Now, I did skip over a little detail. Let's come back and fill in that little blank. This was not presented to us as a graph. The question here came to us as, hey, check out this equation. Right? How would you parameterize the surface defined by this equation? So, well, when that happens, if you can solve for one of the variables, go ahead. Right? That's the only sort of little missing bit, and you'll notice I can totally solve for y here. So go ahead, you solve for y, and now you have it as a graph, and as previously discussed. Is that all right? Do be careful. You look at this equation right here, and it's tempting to say, okay, well, I want to solve for z because, alphabetical order and all, right? You try to solve for z, you see z outside of the exponential, inside of the exponential. You know you can't solve for z. That algebra doesn't work that way, right? And they kind of throw up your hands, right? But don't forget, you don't have to solve for z. You could solve for x. Okay, we can't solve for x either. Or you could solve for y. Score. Okay. Cool. What if you have a spherical graph? And I'm going to claim that's what this is. This is a spherical graph in the sense that I have solved for one of these spherical variables, right? Instead of having a rectangular variable as a function of the other two, here I have a spherical variable as a function of the other two. This expression right here, cosine phi, that is a function of phi and theta. I don't see the theta. I don't have to see the theta. The theta dependence is super easy. It has no dependence. It's okay. That's fine, right? This is a function of phi and theta. Just a very convenient one. When you encounter this, there's one little tweak that you make to the system, and that is write down the conversion formulas first. So there's our spherical coordinates conversion formulas. And then, again, just kind of plug in rho being this formula. All of these rows, plug in what the formula says they are. And again, victory, we have position as a function of two parameters. Now my two parameters are phi and theta instead of s and t, but that's all good. Totally fine. Everybody happy? Okay. All right. Okay. The next example we're going to talk about, the next example in the notes is this one right here. We are behind schedule and tough choices and all that. This example is, I'm going to call it a little obscure. It is a good tool for your toolbox. If we had that kind of time, we kind of just don't. So this is not an important example. It's actually pretty rare that something like this would come up naturally. I am going to leave it in the notes, of course, because it's still good ideas, and who knows, at some point in the future you might want to look back and think about this. You might be able to have some use for this. But you are not responsible for this example in this offering of Math219, and so you don't have to look at that if you don't want to. If you do want to, please do. I think it's good stuff. If you want to ask me questions in office hours, please do. Happy to help, but you're not responsible for it. Okay, this next one is actually really useful. This comes up a lot. There are a bunch of situations where you're going to parameterize by, as I like to put it, creating a new set of coordinates. Really useful in a lot of situations. You're going to find some of these on the homework, by the way. So here's a big idea. Let's try to parameterize this torus. This thing we call a torus. It's like the surface of a donut. For whatever reason, I entertain myself by imagining this being a great big gigantic space station. I don't know if y'all have seen those sci-fi movies where they have this great big space station and it's shaped like a donut. And the reason they shape it like a donut is because then when they have it spinning, right, centrifugal force creates a kind of an artificial gravity. And that's pretty real physics, right? Perfectly realistic. So let's phrase the question then. If this were a gigantic space station, and if I needed to describe where my house was, or my room, or whatever it is on this gigantic space station, how would I describe the location? What's a natural, convenient, tailored to this surface way of describing location? Well, I wouldn't go around giving rectangular coordinates. That doesn't make any sense. You don't need 3 coordinates to describe where you are in a two-dimensional surface. Spherical coordinates would be just as bad. Cylindrical coordinates, almost as bad. Still pretty bad. So here's what I think would be much more reasonable. A very simple and natural coordinate system is to realize that, and let me just zoom in here on this picture, given a location here, all I really need to know are this angle right there that I'm going to call S, and I'm going to call this angle here T. If you know this angle T and this angle S, that tells you where you are on this surface. And it's tailor-made for this surface, right? Because this surface has kind of a roundness around the z-axis, right? And roundness is very well addressed by angles, and this angle S kind of addresses that roundness. And then, given what your S angle is, effectively that narrows things down to a circle, and well, on that cross-section circle, this angle, measured from the center of that circle, is a good way of telling you where you are on that circle. I mean, another way to say it is you can kind of think of a torus as having kind of 2 different kinds of roundness, and therefore 2 different angles needed to describe your location. What do y'all think about that? Does that seem like a reasonable choice? Okay, so S could be anywhere from 0 to 2 pi. T could be anywhere from 0 to 2 pi. Every point on the torus would give you S and T coordinates. Every S and T coordinates would give you a point on the torus. So, very convenient. All right, now where's the parameterization coming from? The parameterization is coming from just doing some geometry on this, really. So the very first thing I'm going to do is talk about how this point can be understood based on first temporarily talking about this orange point here that I'm going to call P. Now, if I can describe P first, talk about the details momentarily, and then if I talk about how much I rotate from this orange point to get to that purple point, then that'll get me where I need to go. Right? If I understand the orange point and I know how to rotate, that'll get me to my purple point that I want. All right, so two-step process. Let's talk about this orange point first. This orange point, a little bit easier to see, blown up like this. And let me clean up my picture here. That's a great big mess. Okay, so here we go. That point there. Notice that point is this vector plus that vector. And I just have to play some geometry games and figure out what those vectors are. I'm going to leave the geometry, it's geometry and trig, if I can get my thing to cooperate, leave that as exercises for y'all to do. Real quick though, you can see this, this vector here is going to be that. This green vector here, this little green vector, you can see it is going to depend on t. As t increases, that green vector is going to kind of go around in a circle, kind of in the x direction and the z direction. That green vector never points in the y direction. Right? So resulting little bit of trig, that green vector is that. Make sure you can do that. Make sure your trig and your geometry is comfortable enough that you can comfortably persuade yourself, derive for yourself this right here. And so altogether, our P is the sum of those, which therefore is that. Okay, that's the first step. Next, keep in mind, the idea was that once we know that orange point and we want to find, well, what are the coordinates of this result of rotating? How do I rotate that around? Specifically, notice I'm rotating around the z-axis. I just need to write down the formula for the linear transformation that does a rotation around the z-axis, sine angle s. And now that's another little exercise for y'all to think through. And y'all will recall, I'm sure, that I've implored y'all on many occasions to make sure that you're rock solid on your standard geometric linear transformations like rotations and reflections. Right? And the big idea, of course, is that the columns are the images of the standard basis vectors. So you just need to think about your standard basis vectors. Oh gosh, let's see here. Standard basis vectors. Think about what happens when you rotate them. Do the resulting trig that you get when you rotate these vectors. And those results become your columns. So again, make sure you can do that. Make sure you're good to go. But this is the result. There's your rotation matrix. And now it's all over but the shouting. We've already figured out how to write the orange point in terms of S and T. We know how to write this rotation in terms of S and T. So to get to my point on my torus, I'm going to start with the orange point. I'm going to apply the dark blue rotation, and we win. So, oh gosh, let's see here. I want that erase. Come on, erase. I wonder if that was weird. Okay, so here was our orange point that we derived. Here's our dark blue rotation matrix, and you multiply those together, and there's your parameterization. So, a little bit of an ugly result, but it gets the job done. And this. By the way, this exact formula is in the book. And in the book, they just say, here it is, right? With no justification of where it comes from. This is where it comes from. Okay. All right. That's a good place to draw the line. Y'all have a great weekend. See you on Monday.